Hello, and welcome to this video where we will be continuing our conversation from deterministic system to probabilistic systems. So a quick review of what is deterministic systems. As the system was represented, state was represented by vectors which are always L0 normalized. Only one state of occupation at a time, so you can either carry a value of 1 or 0, but not both at a time. And the state of system was always deterministic, that we always knew whether the system is in state 1 or 0. So that's deterministic. Now, if we go further from that concept and look at what is probabilistic systems, then what we are looking at this screen is that all the numbers represented in the green circle are the probabilities of finding the state in that particular circle or vertices that we have called it. Now you can have finding the system one half in the left topmost vertex, 1/4 in the right topmost vertices, and examples like that. Now, if you look closely and keep observing it, then, as we have said in terms of deterministic, that we may end up finding the system in state of 1, which is on the top left vertices. So in probability, we have not the short guarantee of finding the system in that state, but the probability of having the system in that particular state. What we can see that the probability here can also be represented in the vector notation, with the probabilities acting as the values of the vector, what we have seen as coefficients. So here we have 4 values or 4 coefficient for probability. Now, what we have seen in the deterministic, which is L0 normalized, that only one of the elements of the system will be active, represented by 1, and rest are zeros. In terms of probabilistic systems, the marble must be found. For example, your system must be found somewhere, but the constraint is that the sum total of all the probabilities, or if it is represented in the percentage, then the sum total of the percentage should either be 100%, and the sum of the probability should always be 1. Now, looking at the operator, what we can use to change the probability values, the operator must be double stochastic in nature. And what does it mean is that your rows and columns both should have the L1 constraint, which is that their sum total should add to the value of 1. In achieving or in developing the double stochasticity, it has to be noted that it is not just the state of the system going from one state to another adds up, but also the reverse, that when the system comes from the other way around, for example from 1 to 2, but also from 2 to 1, the value should be add to the L1 normalized constraint. Now let's take an example where we will be transitioning from an initial state represented by the vector x0 having the probability 1/2 for having the system in the first vertices, and 1/2 having the system in the fourth vertices, and 0 for rest others, and we apply the matrix which will evolve, or which will transition the system from x0 to x1. Now, what is to be noted here, that after applying the matrices or the operator, The new state also manages is L1 normalized, and all the elements, the probabilities which are represented in terms of probabilities, lies between 0 and 1. Now, what we have said is that the reversing arrows, or for example, moving the system state from 1 to 2, can it is also possible to achieve moving the system from 2 to 1, and that is achieved by applying the transpose. So here, for example, transposing the operator, what we see, we can go from x0 to x1, but we can also apply the condition of putting the reverse of the matrix, that is the transpose, on x1, and we can go back to x0. Now, this way of acting with the transpose on a system teaches us something about the time symmetry, where we have the capability of forward and backward time evolution, which is the time reversal symmetry. And this is one of the utmost important concept in quantum mechanics. For example, as we have seen in the previous video, when you apply an AND operator, then when you got the output as 0, it is impossible to determine whether the value is from 0, 1 or 1, 0 operator. But in this case, in terms of probability, you can apply transpose to go back from state 1 to 0, like the way you came from state 0 to 1. Now, in terms of relation to deterministic system, as we have also seen that deterministics are L0 normalized, but probabilistics are L1. In a real world, stochastic vectors is an unknown attribute, is an abstract concept. It is approximated. And how do you approximate it? Is by you redoing an event again and again and counting the outcomes. So for example, you flip the coin, you draw a dice, and a thing, and you continue to put these events, repeat it n number of times, and at certain moment you you count the distribution of what is the outcome, and then you approximate using L1 normalization to some probability distribution, which should add up to 1. So an stochastic vector is a probability distribution over all the basis states, so which is L1 normalized. So for example, the number of the coin flips that you do, at the end of it, whichever is the distribution of head and tails, it should end up after a certain number of events to 1. A deterministic vector, on the other hand, is a count distribution of all basis state, but which is L0 normalized, which means when you flip a coin, you know deterministically that it will be either head or a tail, and not a combination of head or tail. Therefore, states are stochastic vectors. Operators in probabilistic systems are double stochastic matrices. For example, rows and column, both should be L1 normalized. System remain in L1 normalized probabilistic until you measure or it is unveiled. It then becomes deterministic. So you know the final outcome is either head or a tail, but not both. I'll stop here. Thanks for listening, and I'll hope to see you in the next video. Thank you very much.